Okay, so how is everyone today? Good, I hope. It's not.
Oh, no, it's great. How's your day?
Pretty good.
Did you go trick or treating with the kids?
Oh yeah.
They have a great time.
Well, how could they not? Candy,
My dad took all my candy when I was done.
running around. Oh yeah.
Never trusted. We just got to have the experience.
Well, I just I don't let them have the hard candy that gets stuck in your teeth. Yeah, because it causes cavities. But they can have anything else. Okay, so last time we were talking about polynomials. We're still talking about polynomials. And it's November. Wow. Oh, well, I haven't verified this, but I feel like 100% certain that actually Walmart already has their Christmas decorations out. Okay, well, they came out the day after October last year, or at day, yeah. Did you have a question?
And right at midnight, like Walmart puts like the Halloween, like everything like half off.
Yeah.
Right at 12 o'clock.
Don't fall for that capitalist trick, guys. The whole month avoiding it. Don't. You didn't save $5, you spent $5. You know what I mean?
Okay. I'm gonna use my executive authority to steer us back to algebra. Okay. So specifically what we did is we said, okay, so here's a polynomial. So something like this. And then in here, so something like that. So what we did is break, in a sense, polynomials into two regions. We referred to the outside bit as the global behavior, and then this local wiggle part as the local behavior. So in particular, this picture right here, you should be able to tell me from this picture whether or not this polynomial has even or odd degree. So which is it? Odd. Why? Why odd? Well, because the left side is going down and the right side's going up. So anytime that the left and right behavior is opposite, then the polynomial is odd. If the left and right behavior is the same, then the polynomial is even. So another thing you can tell from the global behavior is the sign of the leading coefficient. So what is the sign of the leading coefficient? Positive. It's positive. Why is it positive? Because the right side's going up. Okay, if the right side were going down, then the leading coefficient would be negative. Okay, so we can tell all that from the global behavior. Then we were discussing the local behavior. So the first element of local behavior that we were discussing was, so consider, for example, the polynomial a multiplied by x minus c1 multiplied by x minus c2 multiplied by x minus c3. So we have a polynomial, but it's written in this factored form. What I want you to tell me is what values could I plug into this polynomial? What inputs could I provide so that the output would be 0? C1, C2, and C3. Because, for example, if we were to plug in C2, this factor right here That'd be C2 minus C2, which is 0. And it doesn't make any difference what the other ones are because they're all going to be multiplied by that 0. As a result, if you were to sketch this, you'd know it would end up having to look something like this. C1, C2, C3. So suppose it looks like this. Okay, very interesting. So now, from this picture, you should be able to tell me what is the sign of A? Negative, because A, this value right there, is the leading coefficient. If you were to multiply all these terms out, all these factors out, and collect like terms, it would be x cubed, and then multiplied by a, ax cubed. And since the right side's going down, it must be the case that a is negative. Okay, so now let's compare that. Let's compare that to this polynomial. G of x is a multiplied by x minus c1 squared, say, and then we'll leave this one x minus c2 like that. And then how about x minus c3 cubed? So what I want you to observe, comparing f and g, is that notice also if you plug in c1 into g, if you provide input c1, then the output is also 0. Okay, but the difference is that now we have this factor is being squared and this factor is being cubed. And the question is what effect does all of this have? So before we answer that, I have a question. This polynomial, what is its degree? So what's the degree of this one? 3. What's the degree of this one? Not 9. So it will be, so how did you get 3 for this one? Okay. And the reason why it's going to be 3 in the end is because you're like counting, like this is going to be 1 and then 2 and then 3. So how many of them are here? There's 6 of them, right? Because this one needs to be counted twice. 1, 2. This one needs to be counted once. What's its exponent, by the way? 1. And this one needs to be counted 3 times. So if I write the implied exponent right there of 1, then 2 plus 1 plus 3 is 6. That's its degree. Okay. So that's interesting. So that tells us about the global behavior. What must be true? We're gonna sketch G in a moment. But the fact that it's degree 6 tells us something about its global behavior. Or down. So both the left and right sides have the same behavior. Okay. So, another thing that we said last time is we talked about when factors have exponents, what effect will this end up having? Okay. So, if we were to ignore temporarily these terms right there, so those ones that I'm covering up, so A multiplied by that thing being cubed, then this would be a cubic. This would be a cubic. And it would look like an S-curve. So the fact that this is a cubic means that when we come to C3, we need to pass through it shaped like a cubic. So what I mean to say is this: if we're going to C3 like so, then we're going to pass through it shaped like a cubic. Okay. So now, here's the going to the left. This C2 is the next zero. The next zero. So we're going to have to bend. We're going to have to bend down and go through and deal with this C2. But notice, what's the exponent for the factor that deals with C2? 1. So we're going to pass through C2, not like a cubic, but like something like a polynomial of degree 1. So what is the shape of a polynomial of degree 1? A line. Yeah, a line. So we're going to pass through C2 kind of like a line, not with a curve, but pass right through it. So something like that. Okay, so now the curve has got to bend to reach this last zero, so we're going to have to go back up. And then the question is what are we going to do when we get there? How are we going to interact with this zero? Okay, so you have to consult the formula here. So what's the degree here? Degree 2. And what do degree 2 polynomials look like? Like parabolas. So we're going to have to deal with C1, but we're going to have to not cross the axis, so it's going to end up looking like this. So we come up to C1 like a parabola, and then go back down. So what I want you to observe is that if you were to cut out a little window around C1 and just look in that window, then just that bit looks kind of like a parabola. And if you were to cut out a little window around C2 and just look at that bit, then that looks like a line. And finally, if you were to cut out a little window right here around C3 and just look at it, then that is like a cubic. And they're in correspondence here. Okay, so any question about this? So this one is like a parabola, this one is like a line, and this one is like a cubic. One thing that I want you to be able to tell, even at a glance, is that when a factor has an exponent that's of even degree, so like 2, say, then you're going to end up on the same side as the axis. You're going to bounce off. Okay, whereas when the exponent is odd, like 1 and 3, you're going to cross. So because this exponent is 1, that's a crossing. And furthermore, because it's 1, it crosses like a line. Because this exponent is 3, you're going to cross. But because it's 3, more than 1, it's going to cross like a cubic. Any question about these? Okay, so let's try another. Suppose I give you sketch of a function. Say this is say 3, and this 8. Something like that. So, I could ask, well, what's the parity of the degree of this polynomial? Is this polynomial even or odd? It's odd, right? Because the behavior is opposite. Okay. What is the concerning x is equal to 3? Because you can see that there's a 0 there. Concerning the 0 at x is equal to 3, what is its parity? So the parity of the 0 at x is 3. So what do you think? So in the first place, well, what is its parity? It's odd. Why is the parity of the 0 at 3 odd? So is this obvious or too subtle? Because I'm not getting a response. Yeah. Yes. So which one? It's unclear. Okay. That's fine. I can deal with that. So what I'm asking you to do from this prompt is put a little box. You know, you don't literally have to put a box. You can just do it in your mind's eye. Put a little box around that 0, and then ask, well, when it comes to drawing this, at that 0, do you cross or do you bounce? You cross. Okay. So, therefore, the parity is odd. Okay, that's what it looks like to have an odd 0, a 0 with odd parity. Furthermore, that means that the parity could be something like 1 or 3 or 5 or 35 or something like that. So it's definitely odd, and you can't really tell from a picture, or it's hard to tell from a picture, but do you have a guess about what the parity might be? 1 or 3, or what do you think? Probably 1. So odd and probably 1. Probably 1 because it goes through there, you know, flat. Yeah, that's pretty flat. If it went through there like an S, then it is probably 3 or more. So how about the same question, but at x is 8? Yeah, even. Why even? Okay, very good. And parabolas are even. So in that box, you don't cross that 0. You don't start on one side of the axis and end on the other side. You bounce off of it. So this is what even looks like. Okay, probably 2. Okay, very good. So how about turn the problem around and say, how about f of x is -3 multiplied by x plus 4 to exponent 2 x plus 1, we'll make this, I don't know, 3, and then x minus 2, and we'll leave that one. Okay, so my first question is what is the degree? No, let's do it like this. Let's do purely analytic things. So what's the degree? I want to know that. What is the sign of the leading coefficient as x? Sorry, as x goes to the left, what does y do? And as x goes to the right, what does y do? Okay. So how about it? What's the degree? 6. And how do you come to that? Add up all the exponents of the individual factors. So this one plus this one plus this implied 1. That's 2 plus 3 plus 1 is 6. So the degree is 6. Okay, what's the sign of the leading coefficient? Negative. Okay, good. So in that case, what about these two? So how about this one that I'm pointing at? It's going to go, y is going to go to negative infinity. Okay, so now, how do we know that's going to occur? Because what's negative? Well, this right here, this statement is a statement about the global right behavior. So what I mean is the part of the global behavior that's on the right. That's what this one is saying. And we know it has to be going down. Why do we know it has to be going down? Because the leading coefficient is negative. Okay. So this other one is about the global left. And so what is that going to be? So what's it going to be? To negative infinity. Okay, because we know that this one's going down because the sign of the leading coefficient is positive. And that's the right side. We know that the left side is going to be the same as the right side because the degree is even. Okay, good. Any question about this? Okay, now that we know these were all questions about the global behavior. Now that we know that, I want you to please provide a sketch. Okay, so the aspects of the sketch that I'm looking for is all of the zeros need to be in the correct place. You have to have the local parity correct. Local parity of each zero. And you also have to have the global features correct. Okay. So I'll give you a moment to do that. Okay, so in the first place, how many zeros are there? Three of them. Okay, I agree. And what are their values?
3, 2, or sorry, -3, or -4.
Mm-hmm.
-1, +2.
Okay, very good. Okay. So now, in a sense, we've got to draw, you know, a nice, smooth-looking thing that wiggles around, interpolates these points, but it's got to do so in a very specific way. So I find that it's easiest to kind of sketch the global behavior first, okay, just to give myself something to look at. So globally, we know that the right arm needs to be down and the left arm needs to be down. That's what we know. So I know it's got to look like this somehow. So I know that much. And now that I know that, the rest of the trick is just going through the zeros, but doing so with the proper local parity. So I did it right to left last time. Let's do it left to right this time, just to be different. So going through -4, or dealing with the zero -4, are we going to cross or bounce? We're going to bounce. How do you know we're going to bounce?
Because it is to the second degree,
Mm-hmm.
so that means that it has like a shape of a parabola.
Like a parabola. Very good. So we go up to it and then bounce off of it. Okay, so now we bounced off of it, and now we're going to have to come back to meet the next zero. That one right there. When we come to it, will we bounce again or will we cross? We'll cross. Okay, good. Will we in what kind of fashion will we cross?
That like a snake thing.
Like a snake, right? Like a cubic. We won't go straight through it like a line. Rather, we'll do kind of a we'll go through it like a cubic. So we'll come up to it, get a little bit flat, come away from it a little bit flat, and then continue going up. Okay, so now we're going to have to come back down. We're going to have to come back down to that last zero. Now, even without looking at the formula, I know for sure, supposing I've done all the rest of it correct, surely we have to cross 2. Why do we surely have to cross 2?
Because our global right side is going down.
Right, because we
Past the y-axis.
right, we've got to come down here and meet this one. Now, you might say, well, what if we just bounced off of 2 and then came back down and met that bit? That wouldn't work either. Why would that not work? Well, I'm saying, I agree with that, but I'm saying suppose that I ignore the formula for a minute.
You would have to have another 0 to come back down.
You'd have to have another 0, right? If you bounced off of 2 and then turned to go meet this one, that means you'd have another 0 over here. So the only way that, because there are no other zeros than these 3, you simply must cross at 2. And furthermore, how are we going to cross?
You're going to cross straight through it.
Straight through it, like a line. So something like that. Polynomials don't really do that, but I kind of ruined myself there. Okay. Any question about this? So what I mean is that the zeros are in the correct place. The local parity is correct, right? Even parity, degree 3 parity, degree 1 parity, and the global parity is correct too. Good. Any question about this? Okay, good. These are kind of fun. They're kind of like a puzzle. You got to work your way through to the answer. Okay. So, here's another bit. So here's a statement. A polynomial with n zeros has degree at least n. Okay, let's try and understand. Let's try and understand this. So let's consider degree 2. Now, what is the shape of things of degree 2? Parabola. So I'm going to do 3 different examples here. So 1, 2, 3. So just for sake of concreteness, let's imagine a parabola that opens up. Can you imagine for me a parabola that has 2 zeros? That is to say, crosses this horizontal axis twice and opens up. You can't imagine it? How about this one? So we do it twice, right? So 2 zeros. So that means that this is at least degree 2. Sorry? You'll wait? Okay. So, well, can you imagine if I were to move this red around, can you imagine a situation where this parabola would cross, would have no zeros?
Yes.
Yeah. So how do I do it? Yeah, just draw it up there. Okay, so this has no zeros, but it is still degree 2. Can you imagine a situation where there would be exactly 1 zero?
Yes.
Now, how do we do that?
Just bounce off.
Like we've been doing all day. Okay, so like this. Okay, so 2 zeros, 1 zero, 0 zeros. So this is degree 2. Let's look at degree 3. And again with 3 examples. So not yesterday, but Monday, we were looking at a cubic. We were looking at the cubic polynomial x cubed minus x, and it ended up looking something like this. So 3 zeros. 3 zeros. Now this goes all the way down. So all the way down. Can you imagine a situation where I'm able to grab hold of this red and move it up, say, and can we make it to where there's just one zero? Yeah, we could, lift it up high enough to where it looks like this. So just one. And then can you imagine a situation where we could get 2? So this is 3 of them. That's 1 of them. Is it possible for us to get 2?
Yes.
Yeah, by doing what?
Moving down a little bit more because that second zero we
Exactly. So come down and then bounce that one off, like so. Okay. Interesting. So if I were to present, what I want you to see from this is that if I were to present to you a polynomial that has say 4 zeros, it would have to be degree at least what? At least 4. But it could conceivably be more, right? So for example, this has no zeros, but it's degree 2. This has 1 zero, but it's degree 3. So now, let's take this sentence, and I want to say it in another way. So English as a language is subject, verb, object, SVO. So the subject of this sentence is a polynomial with n zeros. That's the subject. The object is the state of having a degree at least n. Okay, and the verb is has. So what I'm going to do is I'm going to switch the positions of subject and object and say the following. A polynomial of degree n okay, and now I want to complete this sentence.
N0, that's right, N0.
Okay, so that's pretty close. Has something in zeros. At most. At most. Okay. So have a look at this. This polynomial is degree 2. And imagine all the different ways you could move it up and down. What's the maximum number of zeros you could possibly achieve? 2. So this polynomial of degree 2 has at most 2 zeros, but it could possibly have less. Similarly, this polynomial is degree 3. What is the maximum you could achieve, number of zeros? 3. But you couldn't get any more than that. Okay, good. Any question about this? So another one. Besides zeros, another thing this is counting the zeros. So this is a statement about counting zeros. Another item that we count is the turning points. So that is to say the local extrema. Local extrema. So for example, so all of these here, so that one, that one, that one, and that one, those are all turning points. Okay, so this particular one that I drew for you has 4 turning points. This one has 2 turning points. That one has 1 turning point. Okay, so 1. A polynomial with n turning points has degree, and let's see if y'all can complete the sentence. Okay, not in. Let's think. Let's look at the particular examples I drew up here. So how about what is the degree of this one? 2, right? Because I said that these were all quadratics. There you go. So it's not exactly n minus 1 either. A polynomial with n turning points Not n minus 1, n plus 1, right? So this has one turning point, but what's its degree? 2. This one has 2 turning points, and what's its degree? 3. Very good. So so if you have n turning points, then it has degree what? So something n plus 1. How many turning points?
1.
So this has, its degree is at least 1 more than that. So this is degree 2.
I'm thinking of degree as an n.
We're going to write the sentence. We're going to write the sentence in the reversed order in a minute. So this has 2 turning points. So its degree is at least 3. Okay? Oh, I said it. That's what I'm trying to get you to say here. At least n plus 1. So now, to help you understand this, I'll do two specific examples. So how about y is x cubed? So that's a plot that you're required to memorize. And then y is x cubed minus x. That's one that we did on Monday. And let's look at those plots. So the cubic looks like this. Now how many turning points does it have? None, right? None, because a turning point is a place where water would collect. Okay, or if you like, if water could fall up where it would collect. And water wouldn't collect if it was falling down on this one, and it wouldn't collect if it was falling up either. Whereas this one looks like this. Now they're both degree they're both degree 3. This one has 0 turning points, and this one 2. So now let's turn the sentence around, and I'll say that a polynomial of degree n, okay, and then you finish the sentence.
Has turning point at least n minus 1.
Almost.
At most n minus 1?
At most. Has at most n minus 1 turning points. And the way to it can be kind of when you're, I encourage you not to try to just memorize it like as a phrase. Like I in high school, I can remember I had to memorize, like, I forgot what. I already forgot what it was, but it was something like some part of like Shakespeare's play or something like that. I had to memorize this much. I'm not sure why that was useful. Please don't try to do it that way. Try and think about, think about a specific example. Take, for example, a quadratic, because you know that one. Okay, its shape is a parabola. How many turning points does it have? 1, and it's degree 2. So a polynomial of degree 2, is there any way you could get it to have more than 1 turning point? You couldn't possibly do that. So degree 2, at most 1 turning point. And generally, degree n, at most 1 less than that turning point. Good. Any question about this? Okay. How are we doing on time? Still good. Seems like there was one other thing. Okay, so I'll bring up what it is we're going to do next time. So next time, on Friday, we're going to solve a problem like the following. So this is a problem that you learned how to do in 3rd grade. So in 3rd grade, you were set to the task of dividing and to compute quotient and remainder. So what I mean is, for example, it's true that if you do 21 divided by 5, that's 5.25. That's true. But I'm not interested in that 0.25 business. Rather, you might remember your teacher saying, find the quotient and remainder when this is divided by that. Okay? So, and that sounds really boring, but you can get 3rd graders to, you can have them paying real close attention if you say, okay, class, you'll notice that there's a pile of M&Ms in front of each one of you. Now you have their attention, right? Suppose that we do this, that you have 23 M&Ms in front of you, and I say, okay, I want you to break them into groups of size 4. How many groups of size 4 can you make from 23 M&Ms? 5 of them. That's how many groups you can make. And then once you've done that, what's left over? 3 are left over. So the number of groups you can make, this is the quotient, and the number that's left over, this is the remainder. And it looks like this. So let's do a slightly bigger one. So how about divide, say, like 127 by 4. The way that you do this in grade school, if you were in my class, then the teacher would say, okay, class, now we're going to put the 127 in the house and the 4 is outside the house. And 4 wants to come in. How many times can 4 go into 1? It cannot. So then, instead of taking just one digit, let's take another. So we'll take that one and that one. And then ask ourselves, okay, 4 wants to come in. How many times can 4 go into 12? 3 times. So then, you write a 3 right here, but understand that that 3 really means 30. So we're going to take that 3. It realizes it's in a math problem. It jumps off the house in despair, I guess, and then hits the 4 on the way down. You write a 12 right here, and then you subtract them. So how much is left when you do 12 minus 12? 0, and then you pull the 7 down as a remainder. So now 4 wants to come in. How many times can 4 go into 7? Once. So you write the 1 right there, and then the 1 jumps off the house, hits the 4 on the way down. 1 times 4 is 4. You write it right there, and you subtract. 7 minus 4 is 3, and now there's nothing left to pull down. Do you observe that this value is less than 4? So that means we couldn't possibly make another group. So the answer to the question is that the quotient of this division is what? 31. That's how many groups we were able to make. And the remainder is what? 3. So what we're going to do next time is we're going to solve exactly this problem, except we're not going to be dividing an integer by an integer. We're going to be dividing a polynomial by a polynomial. Okay, very good. So have a nice Wednesday.